A Tsinghua spin-off on the US Entity List just released the most capable open-weight AI model in the world under a fully permissive MIT license. A one-person project then figured out how to run it on a 25-gigabyte laptop. The whole trick fits in 1,300 lines of C. By the end of this, you'll know why a 744 billion parameter model can run on a machine that costs less than one H100 fan, exactly what only 40 billion parameters activate per token actually means in hardware terms, and the honest speed number. Because it is not fast, and that's not the point. Start with the model. GLM 5.2 shipped on June 13th, 2026. ZAI, which is Jipu AI, which is a spin-off from Tsinghua University that went public on the Hong Kong Stock Exchange in January, put the weights up 3 days later under an MIT license. No revenue clauses, no attribution carve-outs, no regional restrictions. Even though the US Commerce Department added Jipu to its entity list in January 2025. The weights exist. The license says you can do what you want. That combination is the entire premise of this video. The benchmark case for this model is real. On SWE-bench Pro, which tests agents on real long-horizon bug fixes in real code bases, GLM 5.2 scored 62.1%. GPT 5.5 scored 58.6. The Artificial Analysis Intelligence Index ranked at 51, the highest any openly licensed model has ever scored. On AIME 2026, it posts 99.2%. It is not a frontier-beating model across every dimension. On the hardest agentic reasoning tasks, Claude Opus 4.8 still has a clear lead, and GLM 5.2 is verbose, burning roughly 42,000 tokens per task where GPT 5.5 uses 10,000. But it is the strongest open model available today, by a meaningful margin, at a sixth of the cost of running closed alternatives through their APIs. Now the hardware problem. The standard line on running 744 billion parameters locally is, you can't. The Unsloth 2-bit quantization compresses the model to roughly 240 gigabytes. That fits on a 256 gigabyte Mac Studio. A 4X RTX 3090 rig with enough system RAM can handle it. These are not laptops. They're either expensive workstations or machines with memory that most developers don't own. The trick that Colibri found is that MoE architecture contains a loophole. Here's the analogy that makes this click. A mixture of experts model is not one model. It is a dense foundation. The attention layers, the shared experts, the embeddings, plus a routing system that, for each token, selects 8 specialists out of a pool of hundreds. The routing system reads every token. The specialists barely read any. GLM 5.2 has 21,504 routed experts arranged across 75 MoE layers. Each token activates 8 per layer for a total of about 40 billion active parameters. The other 700 billion are asleep. What Colibri does is simple in principle and extraordinarily finicky in practice. It keeps the dense part. 9.9 gigabytes at int4, permanently resident in RAM. The 21,504 routed experts live on disk, all 370 gigabytes of them. When the model needs an expert for a given layer, the engine reads it from disk on demand, using a per-layer LRU cache. The experts it used most recently stay warm in memory. The ones it hasn't touched go back to disk. The OS page cache acts as a free second layer of caching underneath. The bottleneck is exactly what you'd expect. A cold decode costs roughly 11 gigabytes of disk reads per token. 75 layers times 8 experts per layer, each expert about 19 megabytes on disk. On the author's development machine, a 12-core laptop with 25 gigabytes of RAM running WSL2 with a VHDX capped NVMe delivering about 1 gigabyte per second random read throughput that works out to 0.05 to 0.1 tokens per second. That is not a typo. 0.05 of a token per second. But this scales with your hardware, and the scaling table is worth understanding. Native Linux on a PCIe 4 NVMe with 32 gigabytes of RAM, roughly 0.5 to 1 token per second. A PCIe 5 NVMe or 2 NVMEs in RAID 0 with 64 gigabytes and 40 gigabytes of experts pinned hot, 2 to 4 tokens per second. A 128 to 256 gigabyte workstation where the hot expert set mostly lives in RAM, 5 to 15 tokens per second. At the low end of that range, this is async work. Queue a request and come back. At the high end, it is usable interactive tooling. 2 tricks push it further. The first is MTP speculative decoding. GLM 5.2 has its own multi-token prediction head baked into the model at layer 78. It drafts additional tokens that the main model then verifies in a single batched forward pass. On the test hardware, This measured 2.0 tokens per forward, the catch. And this is in the fine print. The MTP head must be kept at int8 precision, not int4. At int4, acceptance rate collapses to somewhere between 0 and 4%. At int8, it runs at 39 to 59%. The readme is honest about this. The second trick, Colibri builds a learning cache. Every session, it records which experts your actual usage routes to. At startup, it automatically pins the hottest ones into spare RAM. The model literally gets faster the longer you use it on the same code base, not by a little. Hot-pinned experts are free cache hits. Cold ones cost 11 gigabytes of disk traffic. The difference is measured in multipliers. The engine itself is the other story worth telling, because it is genuinely unusual. A single C file, around 1,300 lines. No Blaze. No Python at runtime. No GPU required. GCC with OpenMP and AVX2, and you're building it. The forward pass, the actual neural network computation, is validated token exact against the Transformers oracle. It is not an approximation of GLM 5.2. It is GLM 5.2. The author ran 32 for 32 on teacher forcing validation. The code is readable in an afternoon. That is rare for ML inference infrastructure. The project hit 453 points on Hacker News on July 10th. The top comment was, "This is the hacker spirit." The author's reply was, "Anti-res is the number one." That's a reference to the Rita's creator, who independently built a similar disk streaming approach called DS4 for GLM 5.2. Two people working separately landed on the same insight about MoE sparsity at the same time. Setup is 3 steps. Clone the repo. Run /setup.sh in the C directory. It checks for GCC and OpenMP, builds the binary, and runs architecture self-tests. Then /coli convert, which downloads the GLM 5.2 FP8 checkpoint 1 shard at a time, converts each to int4, and deletes the shard before fetching the next. You need about 400 gigabytes of free NVMe space at peak, but the full 756 gigabyte FP8 checkpoint never needs to exist on disk at once, resumable at any point. If you don't want to run the conversion, a pre-built int4 checkpoint is available on Hugging Face. Then point coli model at your model directory and run /coli chat. One thing to set before you do any real work. If you want to use reasoning mode, set think = sign1. The default context is size from your available RAM automatically at startup. You don't have to guess. The honest limits. The Alama tag GLM 5.2 cloud routes to ZAI's cloud API, not local inference, a confusion that has burned people. Llama.cpp runs GLM 5.2 with a dense attention fallback because the DSA sparse attention path isn't in mainline yet, so long context performance there is worse than the architecture allows. On soldered SSD laptops, hours of continuous NVMe reads at full duty cycle will heat drives and should be monitored. This is not a daily driver tool for a machine you rely on for other things. An external NVMe or a desktop with replaceable storage is the saner long-term setup. What this actually is, stripped back, is a proof of a structural principle. MoE models contain a sparsity property that conventional inference engines mostly ignore because they were designed for dense models. When only 5% of parameters activate per token, you don't need all the parameters fast. You need the right 5% fast, on demand, with a cache that learns which ones matter for your use case. The hardware requirement for frontier-class intelligence just changed, not to 0, but from you need a $30,000 GPU cluster to you need a fast NVMe, 25 gigabytes of RAM, and patience. The model on disk, the answer in your hand. That's what Colibri is. No newsletter, no course. Just a free subscribe if watching a 744 billion parameter model think slowly on a laptop made your week.